Bismillahir Rahmanir Rahim. So this is the 16th session of CATE 21. The main topic of this session is climate change and building design. I would like to thank all the participants in this session. This, I assume, is the last session in parallel with another session, and thank you very much for joining us. I will not take a lot of time. I will just invite our first participant to present here, first presenter, Huda. She will be talking about mapping the thermal profile differences between traditional and modern houses in Khartoum and their impact on cooling loads. Over to you, Huda.
Thank you. 1 minute, let me check I am sharing correctly. Can you see my screen?
Yeah, okay.
Yeah, it's there. Yes, it's there.
Yeah. Okay. Hello, my name is Huda El Sharif. I'm a PhD student at the University of Kent, and this paper is part of my PhD in collaboration with Professor Henrik Schonefeld and Professor Marilena Nicopoulou. So Sudan is a hot, dry country. The days are hot and the nights are warm, and that poses a problem. Let me just move this. Can you see Mike? 1 minute, let me just hide this. Okay, so the problem with Sudan is that the nights are warm, and this prevents the thermal mass from cooling efficiently at night. And that makes it very uncomfortable in the evening. So what occupants have done in Sudan throughout the years, and this is a solution that's common in a lot of buildings in the region, is they thermally migrate throughout the area. So they go from the evenings and nights in the yard. 1 minute, sorry, I'm kind of confused with this. So in the mornings, they go to a semi-outdoor space, the veranda, and then at noon, they go indoors into one of the scattered rooms. This is called thermal migrations, and it's possible because of the thermal variety. There's always a space that's cool at any one point. And it was also possible because they lived a communal lifestyle where you didn't have an assigned space. You just moved around and did the activity wherever it was comfortable at the time. Common house types in Khartoum were the traditional house, which is, as you can see here, just your average courtyard house with traditional materials like mud, wood, straw, and natural earth floors. But over time, people wanted more stable materials, so they kept that same design, but they demolished the houses and rebuilt them with brick walls and corrugated iron roofs. So that introduced a new dynamic, which is low thermal mass roofs. We've also had a lot of modern Mediterranean type villas, like the one you can see here to the right. And these villas are concrete frames with brick walls. They really depend on an internal lifestyle with a lot of air conditioners, very similar to what you see in the Gulf. Now, in recent years, all of these types have witnessed a surge in installing air conditioners and using even them for longer hours. This has led to more power cuts during the summer. So I wanted to know, well, since people are staying indoors all the time, what's happening throughout the day in these houses in terms of temperature? But I also wanted to understand, because people have become more modern and they stay indoors most of the time, what's happening with their behavior and expectations and their relationship to the building. The goal was to create a base in which solutions can be created that are based on the interaction of the three key components: the building, the air conditioner, the occupant. So 4 case study buildings were chosen. 2 of them are modern, MT and MM. And you can see MM is quite shaded compared to MT. The 2 traditional houses are TM and TE. And I use both qualitative and quantitative measures. So interviews, a thermal camera, and different data loggers in 4 spaces in each house. And every 15 minutes, I would log the air temperature, the humidity, if the air conditioner was on, if the space was occupied, has there been a power cut, and electric consumption. So the thermal camera showed that the roofs had the most significant impact. And you can see this corrugated iron roof was really hot at noon, but cooled significantly when it was time for sunset. And that's because of the low thermal mass, and also because it's directly exposed to the night air and it releases very easily. But you can see the walls still absorbed a lot of heat by sunset. When you look at the other two types that are prevalent, when people added a false ceiling, it didn't get as hot during the day as the corrugated iron roof, but it also didn't cool as much as the corrugated iron roof because it was no longer exposed to the sky. When you look at the concrete roof, it behaved in the exact opposite way. Rather than getting cooler by sunset, it got hotter because it works like a battery, constantly storing that heat energy. Now, this roof has a split profile because half of it on top was shaded and the other half wasn't. So the shaded half got slightly hotter only by 1 degree, but the unshaded half got really hot. So this really shows the impact of shading and how important it is. Now to look at the internal air temperatures inside. Because the monitoring period had fairly similar temperatures, I used the average over the whole period. And for example, I used 30.9 degrees as my 0.0. And so for example, at noon, outside on average, it was 7 degrees hotter than the comfort temperature. And I made it sure to show the blue spaces are conditioned spaces and the yellow are unconditioned. So first, I compared the two modern buildings, and I found that they generally had a cooling need that was stable throughout the day. So you only needed to cool at the same amount throughout the day. And it really impacted, especially in empty, which spaces had a shaded roof or not. And the unshaded space, as you can see, it got significantly hotter during the day. When you look at the traditional houses, they actually had a high cooling need during the day and a low cooling need at night. It created a very distinct S-shaped curve. When you compare the modern house MM and the traditional house TM, because they were both in the kind of cool period, they were not overheating, but I wanted to explore further what was going on. And I noticed that TM consumes a lot more electricity than MM, and they use the conditioners so much. They use an evaporative cooler specifically. And because they were so dependent on it, they created a humidity problem. And that made these temperatures uncomfortable. So looking at the temperatures alone is not enough. You have to understand the wider picture of what's going on. When I compared the two traditional houses, TE and TM, I found that the air conditioner alone did not explain the differences between them because at the beginning of the monitoring period, they still had a very big difference in their performance, despite the fact that they were built the exact same materials. And the difference is the design. So TM is a deeper building, so there's more shaded internal spaces compared to TE, which is more shallow and has more exposure directly to the sun. MM presented a very interesting opportunity. So the family lived in the first floor during 2020 and moved to the ground floor. And I monitored both periods. So, but you have to put in consideration that 2020 was slightly hotter, the black line, than the red line, which is 2021. So I noticed, for example, the space where the same person moved downstairs was only slightly hotter. So the millennial female, this turquoise, is still fairly similar. It's just 2 degrees hotter than it usually is the year later. But what was interesting is the parents and the boys, they switched rooms. So rather than go down into the same room, they switched. So what was interesting is that in both times, the boys' room was always the coldest, even though it was a completely different room. The reason for that was the boys used the air conditioner for 11 hours compared to their parents who only used it for 2 or 3 hours. And interestingly, the parents actually stayed more in the house than the boys. So generally from the interviews and my observations in all of the 4 houses, males consumed more than the females, possibly because they're less invested in the household. They spend most of their time outside the house and they only come in to sleep at night. The older occupants also consumed younger than the less, and their own explanation for it is because they grew up in poor economic conditions and they grew up that it's important to not consume too much. But I also think part of it is because they're the ones footing the bill. So generally, AC usage was linked to the age and the sex of the occupant. When we looked at, well, how are they trying to conserve energy? 3 different types of behaviors were observed. They either started sharing spaces, and this was especially in areas where the air conditioner was a refrigerant one, where it consumes a lot of energy. So they preferred to just sleep in one space. Another tactic that they used was using one air conditioner to cool several bedrooms by keeping the door opens. And from an AC expert, he said that this was very bad because it consumed a lot more energy than using just 2 separate ones because you're overworking that one air conditioner. And as an extreme measure, some of them slept outdoors, which is only available for male occupants. So when I looked at, well, how are users using the space? I used the data that I collected to predict what were the chances of a space being occupied during the morning, afternoon, evening, or night. And I noticed that unemployed occupants, they use the bedroom at day and night. Retired occupants preferred the living rooms, especially in the mornings and the afternoons. They retired early to their bedrooms in the evening and nights. Employed occupants, it depended on their age. If they're older, they preferred after coming home from work or school to use the living room, while younger ones preferred their bedrooms. And that's mainly because their mode of entertainment is different. The older occupants preferred the TV, while the youngers depended on their phone and the laptop and the internet. But the younger occupants were more dependent on the air conditioner. If it didn't work in their bedroom, they immediately went to sleep in the living room. Overall, what I noticed is that the user did not conform to the traditional Sudanese lifestyle patterns that that researchers described in 2000, which is not that far. So there's been a dynamic shift in how people are using these spaces, but they also don't conform to a Western lifestyle where the house is empty during the day, the living rooms are used after they come back from work, and the bedrooms are used at night. So there's no clear, this is a day space and this is a night space. Now, why is this important? It's important because achieving in an extreme climate like this, it's hard to achieve thermal comfort all year round, all throughout the day. It's better to target when the space is most used. That becomes difficult when that is not a clear, there's not a clear answer for that. All we know is that it's influenced by the occupant's age, sex, but also here what was introduced was the employment status. And generally, Sudanese households are extended households. So you have a mix of older, retired occupants with working ones, with children, and that change is constantly mixing. And you have the older generations that prefer more communal spaces with younger ones that prefer more private spaces. So it's kind of like this constant shifting dynamic within the house. Finally, there was a heat wave during my monitoring period. I want to see, well, how are the users responding to that? That gives you an indication what will happen when climate change increases. All of the solutions were all energy intensive. So they either increased how many hours they used the air conditioner, they either added more air conditioners or fixed existing ones, or even upgraded them from an evaporative cooler to a refrigerant. They set a lower set point, and so if they know there's going to be a power cut in 2 hours, they cooled at 18, 17 degrees rather than their usual 27 to kind of prepare the space. They also use batteries to power fans when there is a power cut, so they can avoid more passive solutions. So all of these solutions actually exacerbate the problem because the power cuts are there because people are using so much energy. And these power cuts always happen in the summer, which shows you that it's really directly linked to the air conditioner and that consumption. So what do we get from all of this? That optimizing the thermal performance for Sudanese household requires a holistic approach. You can't just suggest one solution. So ideally, like the modern house that is compact, it's well shaded, it has a high thermal mass in the fabric. That is a perfect solution, but the problem is it's expensive and it's not accessible to everyone. So realistically, we want to replicate the thermal variety that existed in the traditional houses, but create that indoors rather than, because people don't want to migrate outdoors anymore. So combining high and low thermal mass spaces in a case-by-case basis. So you have to look at each individual family and what's happening with them. The reason this solution is good is because the practice already exists in Sudan. People already have different materials in the house because they expanded over time using different materials based on what was available and what they could afford at the time. So this is kind of regulating the practice that already exists and using it. So saying, for example, this high thermal mass space will be comfortable throughout the day. It's preferred for a user, for example, that stays here most of the day. While this space is low thermal mass, it will be best for a user that only uses it at night. Thank you. That is my conclusion.
Thank you very much, Huda. Very nice, very interesting presentation. And thank you very much for actually leaving us with 1 minute. So I will probably, because questions and answers are at the end of the session. So please hang on until then, so that if somebody has any questions, so they can ask.
Yes.
So I will just invite thank you very much for your nice presentation.
Thank you.
I will now request our second presenter. That is, the topic is biophilic urbanism as a radically new approach to bringing nature into cities. So that's Ghada Muhammad.
Ghada seemed to be not with us.
Ghada is not there. Okay. Can we jump to the third presenter then?
And that is, yeah, Julia.
Julia is around, I think.
Yeah,
yes.
Julia is with us. Yeah.
Yes.
Yeah.
Okay. So, yeah, so let me invite Julia for presenting urban layout for building solar optimization and outdoor comfort balance. Neighborhood strategy in high solar radiation areas. Yes, Julia, the floor is yours.
Hello.
Maybe Huda did not leave. I think Huda, I think he went to exit. Yeah.
Is it released now?
Yes,
No.
yes, yes. Thank you very much for that.
I don't know how I can.
So share screen, Huda. Share.
Yeah.
Then go to your folder.
Julia.
Yes.
It's Julia.
Yes, please,
Yeah.
please share screen. You see a button at the bottom, close to the chat, in between chat and raise hand.
I can't see that.
Yes. So just start share screen, and then you will be able to share it. So you can select yes.
Okay.
Julia, do you see the screen with the bottom icons, and one of them is share screen green? Do you see it?
No.
Do you see all these at the bottom? Participant chat, share screen.
Yes, but
Yeah.
share screen. I
Yeah,
have.
the green one. The green one.
Ah, okay.
Click
Yes.
that.
Yes.
Click.
Yes. You can see my screen now.
Yeah.
Yes.
Good.
Yes.
That's good.
Okay. I start.
And make a full screen also, please. Full screen.
One moment. I think. Oh.
If you start the presentation mode, then it will automatically come to full screen.
You don't see my screen?
Yeah, we can see it, but we see the outline as well. So probably, yeah, it's okay if you want to continue like this. It's also not a problem.
One moment.
Because from PowerPoint, you can change to the presentation mode, you know, when you will change it,
Yes.
then the full screen will be there.
No?
Share screen, first share screen, and then you can change to the presentation mode.
Okay. No.
Good.
Yes,
Very
perfect.
good.
Very good.
Very good.
Okay. Sorry.
No problem. No problem. Okay. Okay. Go ahead.
Good afternoon. My name is Julia Diaz. I'm a predoctoral researcher at the School of Architecture in Seville. I develop research on the field of daylighting and thermal comfort and its relationship with urban configuration and human health. And now I'm going to present our work, urban layout for building solar optimization and outdoor comfort balance, neighborhood strategies in Mediterranean climate. Awareness of energy efficiency of building is commonplace, but a deeper knowledge of the urban environment impact on buildings' performance and inhabitants' well-being and health is required, since urban surround affect outdoor comfort, the proper use of indoor daylight, and the energy consumption of buildings. And as proven by important authors, daylight access is essential to avoid an excessive energy consumption and to improve visual comfort, as well as it can help to improve the occupant health through a proper circadian stimulation. But solar obstruction caused by the urban environment is the main physical factor affecting lighting comfort. Nevertheless, an excess of solar radiation can lead outdoor and build overheating, and thus a further increase in cooling energy consumption. In view of the foregoing, and the aim of this new research is to reach a methodological proposal that allows to optimizing urban layout according to the use of daylight in the Mediterranean area, both in terms of thermal radiation management and luminance conditions. Since the urban configuration in the Mediterranean area suffers from significant solar radiation and thermal oscillation, one of the main factors that affect the urban microclimate in that zone. Therefore, to assess the daylight efficiency of urban design, it's necessary to perform a comparison between solar accessibility inside building and outdoor thermal radiation, which will be affected by the solar potential and the urban heat island effect. For this purpose, urban elements that influence the building performance, urban climate, urban morphology and density, and building form must be integrated in a single calculation by means of a methodological proposal that allows to perform multi-criteria analysis of contradictory or conflicting aspects, a complex but an essential challenge. So the methodological proposal must allow to carry out complex analysis, larger scale analysis like urban scale, by carrying out a multivariate analysis of different aspects like outdoor thermal comfort, energy efficiency, or daylight access, in which numerous parameters, design urban parameters, must be taken into account. And for this purpose, the coupling of the different simulation engines in urban building energy modeling for a multi-criteria analysis and optimization in a single calculation is needed. And that's possible thanks to Grasshopper and Ladybug tools. Grasshopper is a visual programming language that allows the assessment of complex urban systems through a parametric workflow. The parametric design method could be defined as a fast way to generate multiple design solutions and configuration by varying the values of the input parameters of the initial design model. So the research calculation procedure is based on a workflow through the modeling software Rhinoceros 3D using Grasshopper. Then the integration of different parameters, factors, and metrics is carried out in a parametric workflow based on the open source plugin for Grasshopper, Ladybug Tools. Ladybug Tools is a family of components for environmental analysis in Grasshopper, in which simulation engines are coupled, allowing complex calculation to be taken more efficiently in terms of computational costs. So we will use it to enhance the lighting efficiency of building in an urban fabric, as well as to establish design guidelines for cities from the study of climatic and morphological conditions at the neighborhood scale. For this research, only the following simulation programs have been used: Radiance, Energy Plus, Open Studio, and Urban Weather Generator, UWG, through Ladybug Tools using Ladybug, Honeybee, and Dragonfly plugins. In this way, daylight evaluation was carried out using the plugin of Ladybug Tools Honeybee. Honeybee allows the evaluation of indoor daylight by connecting the Grasshopper visual programming environment with validated lighting simulation engines for ray tracing, radiance, and dazing. For its part, Ladybug imports the Energy Plus WADA file, LPW, into Grasshopper. And then Dragonfly plugin allows UWG software coupling, which transforms the rural WADA data, generating a modified WADA file. And finally, Honeybee allows the evaluation of outdoor thermal radiation by connecting Grasshopper workflow with Open Studio and Energy Plus. So that Ladybug tools make multi-criteria analysis possible. As evaluation method, the light potential is quantified using the metric both spatial and dynamic introduced by the Luminary Engineering Society of North America, Spatial Daylight Autonomy, SDA. SDA metric indicates daylight sufficiency, defined as the percentage of a surface area that exceeds 300 lux of illuminance during 50% of the occupancy time. Nevertheless, a control of a thermal increase in temperature caused by solar radiation is needed. Thus, a correct evaluation of the hydrothermal and microclimatic conditions of the urban context is necessary. Until now, this analysis has generally been carried out without taking into account the urban environmental effect produced on the climate, the urban heat island. Urban heat islands indicate the environmental modification produced by the effect of urbanization in a specific territory, and its clearest effect is the increase of the air temperature during the night with respect to the surrounding rural environment. This environmental modification is taken into account thanks to urban weather generator, so that produce a modified water file generated from the rural environmental file. In this way, we can simulate the thermal conditions on the urban setting and the study. Once the modified urban weather file is obtained, the real urban thermal radiation is analyzed by evaluating the mean radiant temperature, MRT, in the outdoor environment in July, the warmest month of the year. MRT is defined as the uniform temperature of an imaginary enclosure in which radiant heat transfer from the human body equals the radiant heat transfer in the actual non-uniform enclosure. And the use of this metric is because the analysis focuses on controlling the potential temperature increase from solar radiation outdoor while seeking to maximize solar access in the buildings. So, as I said before, the evaluation was carried out using Ladybug tools in order to assess which urban configuration is more favorable in this sense. And the application of the proposed methodology has been carried out using a small sample of study located in the city of Seville in Spain, which has a significant percentage of its contemporary buildings without a severable adaptation to the local climate conditions. And for the analysis, we have chosen a typical urban expansion configuration. And the figure shows the digital workflow developed for this small application study, as well as the input data, lighting, and thermal metrics and plugin that materialize it. And the geometric model has been performed using a Raynaud 3D. Once the urban geometry to be analyzed has been obtained, it will be parameterized using Grasshopper to perform the subsequent urban layout analysis and optimization. And in turn, the water data file of the location and the study was imported in Energy Plus format. And for its part, the simulation parameters combine both static and dynamic parameters. Static parameters are those that establish the climatic conditions and define the morphological parameters, which are intrinsic to the urban fabric to be analyzed. And dynamic or control parameters are those that determine the purpose of the evaluation, being relating to the performance and defining parameters of light and thermal efficiently, which will vary their values to be able to quantify their impact. And the sample case application, only two dynamic parameters have been introduced, orientation and height-width ratio. Two orientations have been considered, considering say 0 as north, southeast, west orientation of urban block, and 45 as northeast, southwest, northwest, southeast block orientation. In addition, street widths were considered, generating different urban canyon proportion between the range of 4 to 1/2 height-to-width ratio. And the results of the methodological example show between the range of 4 to 1/2 height-to-width ratio a direct relationship between urban canyon and daylight accessibility. The lower height-to-width ratio, the higher the SDA metric. And for its part, orientation not significantly affects solar accessibility according to this location. Likewise, the proportion of the urban canyon equal to or greater than 1 had practically no effect on the MRT. However, for lower ratios, MRT increases. Orientation also had no significant effect on the outer average MRT. However, if we analyze the detailed behavior of each orientation, we observe a significant temperature difference between each orientation and north-south or zero-block orientation. And nevertheless, in 45-block orientation, we achieved similar temperature values on all facades. From the results of this limit-state case study, it can be concluded that a lower proportion of urban canyon in the urban fabric will notably improve the solar accessibility of the buildings in urban configuration without significantly varying the outside MRT if this proportion is equal to or higher than 4-5 ratio. Therefore, regarding the proportion of the urban canyon, 4-5 ratio allows to obtain a more acceptable indoor solar access, while the outdoor thermal radiation is controlled. In addition, 45 orientation seems to be more favorable since it provides a more uniform thermal behavior in all facades of the block. So this study presents an experimental methodological proposal based on a parametric workflow through Grasshopper and Ladybug, and the results obtained in the case study presented prove the method variability of such workflow to determine a set of environmental design criteria at urban scale from a multi-criteria analysis that can be further validated with real environment on-site tests. And in conclusion, this new methodological approach can contribute to perform more complex analysis at urban scale with the possibility of introducing numerous parameters and variables to achieve more solid studies in a faster and easier way thanks to multi-objective optimization and the coupling of several simulation engines in a single workflow. Finally, I would like to thank you very much for your attention.
Okay, thank you very much, Julia, for a very interesting presentation. I think you, it's very nice to see a lot of, like modeling approach and talking about, but some of the questions, of course, I have, maybe I will ask them later, but I would like to invite other participants if they have any questions from both the participants, because I don't see the, oh, Liliana is there.
Liliana is there. Yeah.
Liliana is there. Sorry. Because I thought maybe she's not coming, so I was moving straight to the question answers. But anyway, that's very nice that we have our third presenter of this session. Actually fourth, but one was missing. So welcome, Liliana, to present achieving comfort and well-being in hot and humid climates.
Doctor, may I ask, Liliana, are you from Texas A&M?
Yes.
Oh, very good. I was there a long time ago, so say hi to everybody.
Thank you. Yes, I will.
I got my PhD from Texas A&M.
Oh, really? Okay. I can start sharing my screen. Oh, hold on 1 second, please.
Yeah, no problem. Take your time, please. Take your time.
Liliana, do you see the share screen icon?
I think she logged out.
Yeah. Dr. Ahmed? Dr. Ahmed? Dr. Ahmed? Can you unmute? Unmute? Unmute, Dr. Ahmed.
Yes, Professor Aoni.
Yeah.
I think we can continue with the questions and answers. Of course, you will be holding this session for questions and answers. So if you please conduct this session for questions and answers. If in between, if Liliana appears again, then we can continue with her presentation. We still have time.
Okay, so we have the questions, the chat. We have several questions. First of all, the question actually was given by me to Huda. this is my question. Can you give some details about correlating interviews with recorded data?
Okay, so with the data, first I have an initial round of interviews, and then I start collecting the data. So sometimes the data correlated well with what I was seeing in the interviews. For example, in one of the houses, they said they use this room during the day and this room they share it during the night because of so and so. And then I found from the loggers that yes, that was the case. But sometimes the data conflicted with what they said in the interview. So in one of the houses, they said, oh, we never use this living room. It's barely used. But when I looked at the data loggers, it was actually used very heavily quite at night. And then there was a period where it was used also during the day. So I have to go back and interview again. So when it was used during the day for a short period, it turns out they had a big family change. There was a newborn. They had a lot of guests, and that was their living room was used during that period. But that's not the norm. The norm is the living room is not used. And at night, it turns out that one of the male's bedroom, the air conditioner broke down. So he started sleeping in the living room. But because, like I said, males are detached from the rest of the household, the rest of the household didn't really know. Because he comes in the evenings, he sleeps there at night, like he comes at 1 a.m., 2 a.m., then he leaves in the morning. So this is why it was important to go back and forth between the interview and the data and correlate what was happening. You also asked...
May I interrupt? Can you answer very shortly, please, because there are other questions.
Yeah, sure. The corrugated iron panels, the newer panels are insulated, but it's not very well insulated.
Is the traditional or the modern house corrugated?
The traditional houses. Yes. So the older ones, people who have older ones, they're not insulated at all. It's just a sheet of metal. The newer ones come with insulation, but it's very poor.
So it's not insulated.
No, some of them are not insulated.
My goodness, this is definitely killing the whole issue. If it's not insulated, then we're already at loss. Yeah.
Yes, it's an oven. It reaches 50 degrees inside.
Yeah.
Yeah. And for why I chose these case studies, I tried to pick samples that were as representative as possible. I canceled out several candidates because they were using materials that weren't very common, or they were using an air conditioner type that wasn't common, or they had a family situation that wasn't common. I tried to make it as representative as possible, but also all 4 families are either acquaintances or acquaintances of acquaintances, because it's an extended 2-year study with a lot of interviews, a lot of equipment, and a lot of input from the participants. So it's hard to expect that from a complete stranger.
Dr. Ahmed, can I continue? There's a question to Julia. And I was wondering, this is very interesting work as well, but what are the criteria in selecting case studies? Are you trying to, I mean, like in the previous one, they have 2 completely different types of houses, traditional and in this case, what is the idea of selecting case study and why and how?
We are selected Seville because Seville suffered from significant solar radiation and thermal oscillation. So it's important to control the outdoor temperature while we try to maximize the daylight accessibility inside building. That is the criteria.
Well, I'm trying to stimulate the discussion, so those who did not put on chat now, they could question and answer directly, maybe. Dr. Ahmed, is that okay?
Yeah, please go ahead. Go ahead. Whoever wants to ask questions, definitely we can. Of course, we don't have many participants here in the session, but anyway, if, we have whoever wants to ask questions, then they are welcome.
If there isn't, then I'll ask one more. I'll ask one more question.
Yeah, please, please go ahead. Go ahead.
Okay. Now, in this work, are you trying to show us the capabilities and the limitation of the tools like Ladybug and Grasshopper, or are you using these to test these samples? So what was the objective?
Can you repeat, please?
What I mean, you talked so much about the tools, which
Yes.
is Ladybug and Grasshopper, and it has the capability. So the kind of the title of this is Urban Layout for Building Solar Optimization and Outdoor Comfort Balance, etc., etc. But are you trying? I mean, I don't know much about these tools. Are you trying to show us the capabilities of these tools and never mind what is the work, or the opposite? Are you actually having the case studies of the Mediterranean and merely using these tools, and you could have been using other tools? So what is the objective?
Yes, because this parametric flow have the benefit that of the coupling of different simulation engines for a multi-criteria analysis and optimization in a single calculation, in a single open source tool as Ladybug tools. And in addition, another advantage, or an advantage or disadvantage, is that these plugins are in continuous revision, updates and improvement. We are talking about monthly updates, so it's difficult to keep up to date. Such updates usually involve an increase in computational efficiency, as well as the implementation of new capabilities like new components. And it's with calculation engines that there are validated, like Energy Plus, Radiance. So
yeah. Any more questions, discussion, please? Well, if not, then Dr. I'll ask one more question, if not any, so to keep the thing going. Julia, when we talk about cases in our climate, maybe in Muscat or in cold climate, first of all, I didn't see you telling us what is the problem of your climate. I know it's a Mediterranean climate. Can you tell us what is it more of a problem of overheating in the summer or cooling, too cold in winter? What are the problem you're addressing?
Yes, there are a big thermal oscillation. We have so-called winter and cold and hot summer. So this thermal oscillation is a problem in this climate. And also there are significant solar radiation all the year. Yes.
Well, maybe I could go back to Huda. I had difficulty in understanding what you mean by old or a traditional house and modern. Here in Oman, we talk about traditional as kind of long time. It was built, maybe occupied or not occupied, and basically climate responsive, very little need for air conditioning as compared with modern. In your case, I'm mixed up. For example, in traditional, you would have corrugated metal, which doesn't look traditional to me. So can you describe the characteristic of these two samples, modern and new and old?
Yes. So when I say traditional, I mean like the houses that have been built for the past, for example, 60, 70 years in Khartoum, which is the cosmopolitan center. But like I said, they were originally all built of natural materials, which is mud, straw, and then the same floor plan was demolished and built with more sturdy materials, which is brick and corrugated iron. So that's why I call them modified traditional. They're no longer that traditional. They keep that same floor plan, but the materials is different. And that's why they don't perform as well as the original traditional one. The original traditional one has been rejected because those materials are not very stable. They had to be constantly repaired, and they're seen as something for like poor people. It's not seen as something that someone rich would have. They're very, very rejected. So that's why I call it kind of like I said, modified traditional. But yeah, and they perform very poorly.
Okay, Dr. Ahmed. So now you make your final decision. Should we stop here, or
there's one question in the chat? Do you want me to answer it?
Yes, go ahead.
Yeah, please.
So it says, is it possible to implement old and traditional cooling techniques in new buildings? Is it practical? So in the case of Sudan, the technique that they used was moving through the house. That was the main technique, thermal migration. And that's not possible anymore because people's expectations changed. They become more modern. They want their own bedroom, their own space. That technique isn't really feasible. That's why I suggested replicating the thermal variety that enabled it. So having different comfort areas in the space for different users. So not using the migration itself, but using the variety that existed. Does that answer the question?
Yeah, I suppose so. Well, Dr. Ahmed, I think we could call it an end now, or?
Yeah, Professor Rauni, I think if you don't mind, maybe you can introduce yourself and our department and our architectural engineering program a little bit for the people who are listening.
Yes, very good.
Just to to close the session.
Yeah.
So that would be very nice. I think you have been our mentor for many things, actually.
But I'm outside. I'm an outsider now.
Yeah, well, that's I mean, you are never outside from our hearts, you know. So
well, I would like to thank our guests for beautiful work. I'm sorry that somehow Liliana somehow got disconnected, and Ghada. I know Ghada, by the way. She visited us in the architecture engineering program long time ago. She is a very active person. Well, our architectural engineering program was established 2001, and our system here, we have a department of civil and architectural engineering. So it's two branches. The architectural engineering is not exactly what is known in the United States and Europe, in which it concentrates on engineering technology and architecture. It's really an architectural program with some technology. Our graduate would actually practice architectural design a lot in practice, and they work in technical, like contractor. Usually they don't practice as mechanical engineer or civil engineer. They have the knowledge, but they use it in general. We have a master program now running, and we have active Eco House project. It is becoming a center of activity of sustainability. If you want to have more information, you could contact us or write to me. We welcome collaboration on sustainable design and green architecture. We have a lot of work. Many of my colleagues are working on this. It's a big team. It's actually a College of Engineering project, not architectural engineering, because we have faculty from civil, mechanical, electrical, architectural, and we use it for as a teaching lab now, actually. So you're most welcome to share with us the information and tell us about your work. You've got our addresses. By the way, I think you've got the host, the chair, and the two chairs' emails. You could write to us. You could get more information. And I would like Dr. Ahmed, my dear friend, for sharing this work and following it very well. And I look forward to hearing from you in the future, inshallah.